So, one of the ways I kind of like to talk about the chain rule. Chain rule is used for composite functions. That is when you have a function inside of a function. Okay, like f of g of x. One way I kind of like to think about this, any of you have like an aunt or an uncle or a family member or somebody that they like to like wrap trick presents. Like you've got like boxes inside of boxes. My brother loves to do this to Hunter. He thinks it's hilarious. I think his last year's Christmas present had like 50 zip ties around it. But if you wrap like presents inside of presents, you know, you got this big box, you think you've got something big, and you open it up and it's just another box. And if my brother's wrapped it, it's like duct taped or something. And you just keep getting smaller. So whenever we're taking derivatives, it's like with the chain rule, it is like you are being given a present inside of a present. And to get to what's on the inside, you've got to unwrap the outside first, and then the inside, and then if, you know, we will get to a couple where it's like chain rules inside of chain rules, and then you got to do it the inside again for that there. So whenever we are doing this, I like to sort of make my boxes, my like present boxes, right? So like f right here is your outside function. It's your outside box. And then the g of x is what's on the inside of that. So in order to take the derivative, what you're going to do is you will take the derivative of the f. So notice here that that f became an f prime. But whatever was on the inside stayed exactly the same. You didn't do anything to it. So you do not take the derivative right there. You keep it on the inside. Then, you have to deal with the derivative of the inside box, you have to take the derivative of the inside and multiply it over here on the end. So let's just do a problem to see how this works. Square roots are a place where a lot of this shows up. We had one of these questions before on an FRQ, and we had to use limit definition of a derivative because we didn't know how to do it any other way. But this will allow us to take the derivative of this without having to do limit definition of a derivative. If you have a square root, it is probably going to be in your best interest before you try to take the derivative to change this here to a fractional exponent. Because in general, it is just easier for us to take a derivative of anything when it has a fractional exponent instead of square root. So that's just converting here. I haven't taken the derivative yet. So my outside part of this function is the square root, to the 1/2 power. The inside part is the 2x minus 3. So the way that I'm going to take the derivative for this is I am going to take the derivative of the something to the 1/2 power, right? It is a 2x minus 3, but pretend like it's just something to the 1/2 power. So if I have something to the 1/2 power, the stuff on the outside, I'm going to multiply by the 1/2 out front, I'm going to keep the something the same, and I'm going to subtract 1 from my exponent. All right, so I'll have 1/2 of the something to the negative 1/2 power. That something right there is 2x minus 3. It stays the same. We're not taking the derivative of that part. Okay, that sort of unwraps our outside box. Now we've got to unwrap the inside box. So that is just 2x minus 3. What is the derivative of 2x minus 3? Just 2. So I multiply by that derivative, and that's just 2. Okay, here.
So like this first part with the 1/2, you're like basically doing the same thing, like if it was x to the 1/2.
Exactly. Yeah. So,
It's the whole thing.
yeah, the whole thing. So treat whatever's in that like blue box right there like it's just an x for now. Although we are going to write 2x minus 3. And then the second part is to multiply by the derivative of whatever the blue box is there. Okay. Now, when you get here, they are going to simplify this a little bit. All of this stuff is multiplied together. 1/2 times 2x to minus 3 to the negative 1/2 times 2. So this 1/2 and this 2, I could reorder them so they're up there next to each other. And then 1/2 times 2 would just be 1, right? So that's just going to be a 1. I'm going to write it just because I think it's helpful to see that there is still something there and that just didn't disappear. And then I've got 2x minus 3 to the negative 1/2 power. They could leave it like this. They probably will not. They will probably move this back down to the bottom. 2x minus 3 to the 1/2. And they might even change it back to a square root. Yes.
So I did it like exponents first, and I put that 2x minus 3 to the 1/2 on the bottom, and made it a positive exponent.
Uh-huh.
Put 2 on the top, and then cancel out the 2 to make it 1.
That's fine. Yeah, that's fine.
Does that still work the same way?
Yep, that'll still work the same way. Yes. All right, and so here is our derivative, our final answer for that. Even though technically, FRQ, you can technically stop right here because that is also a derivative for you there.
It's like have to be a rule where it's on chain rule and the square root is 1 over the square root or no? Is that what happened this time?
No, because the numbers do matter a little bit there, like what you have here. So like that 1/2 and the 2 happen to cancel out. But if I had a different number besides the 2, it would not necessarily. So you may have different numbers and things like that. So you will typically, though, if you have the square root of something, you're going to get, like, it's going to be over the square root of that stuff because whenever you do that chain rule, you get a negative 1/2 for that. Okay, let's look at another one. Number 2 is such a tiny one, it almost doesn't look like a chain rule. But it is a chain rule because the outside of this is the sign. The inside is the 8x. Normally we would only have an x right there. So if we are taking a derivative here, we first need to take the derivative of the outside, which is our sine of something, right? When we take derivative of sine, what do we get? Cosine. So we get cosine of stuff, right? That stuff does not change. It stays the same. It's still at 8x. We don't take the derivative of it here, right? So whatever that blue box is needs to still be right there, okay? But then, to do the chain rule, I must then unwrap the blue box. I got to take the derivative of the blue box. What do I get when I take the derivative of 8x? 8. So I multiply by that out here on the end. You are probably going to see them clean that up just a little bit and write it this way. And you could have went straight to this if you wanted. 8 cosine of 8x. You cannot multiply that 8 by the 8x because that 8x is within the cosine. This is just the 8 out towards, like out on the end being multiplied. These are really simple, but kids miss them all the time because they forget that it needs a chain rule. It's so small they forget that they need to do it there. Now, if I had given you example 3 before today, you could have done it. What would you have done? Quotient rule. Okay, you can still do this with quotient rule, and it will work beautifully. I just want to offer another option for you. Okay, if there is only a number in the numerator, this only works if, well, actually, no, it can work other ways, but it's going to be a little more complicated. If there is only a number in the numerator, Then I could just think of it this way as x plus 1 to the negative 1 power. And if I were solving this problem, it's the way I would do it. Instead of using quotient rule, because you can use a chain rule for this, where the to the negative 1 power is your outside, and the x plus 1 there is your inside. Again, it doesn't have to be done this way. Quotient rule still works. If you prefer it, use it. Doesn't matter to me which way you do the problems. So if I take the derivative of this, to take the derivative of the red, the outside box, the to the negative 1 power, multiply out front by negative 1, I got stuff to the negative 2 power. My stuff, so use red for that, for consistency there. Let me go back over it. Negative 1. This is the derivative of my red stuff here. And then the blue box stays the same right here. I don't take the derivative of it. Then I've got to multiply that by the derivative of the blue. What is the derivative of x plus 1? It's just 1. I'm going to write the times 1 over here. That's unnecessary, but just for our notes, we can see that something did happen there. We didn't just forget it. So then they'll clean this up a little bit by just taking that x plus 1 to the second power and moving it down to the bottom and changing that exponent to a positive. And they'll probably leave it like that. They probably will not expand that denominator. They'll probably do that. I think this is quicker than quotient rule because it's like already simplified. If you do quotient rule, you're going to have to do more simplifying. Although, it's not a terrible quotient rule problem either. So this is just another option out there for you. In fact, once I learned the chain rule whenever I was in high school, I don't think I ever used the quotient rule again. You technically never have to use the quotient rule again. You can just move, if you got things in the bottom, you can just move them up to the top with negative exponents, and you can use, sometimes you'll have to do product rule and chain rule together. But you could avoid ever doing the quotient rule ever again. So if you really hate it,
So what if there's like 2 over that?
then you would just have, like, if it was a 2, it would be still a problem that we can do today. I might have one of those here coming up. I got one like that coming up. We'll see it. If it was 2x, then it's going to require a product rule and a chain rule, which we will see tomorrow. So we're not going to go that far today. Okay, here's another one. Now, you guys could do number 4 before today. But what would you have to do with 2x minus 5 to the 5th? You'd have to expand it. So you'd have to Pascal's triangle that all the way out. And then what you're going to see, the problem with that is a lot of times if this is a multiple choice question, the answer is not expanded, it's factored. And then so you'd have to go back and try to factor that, and it would be a nightmare. So, product rule, chain rule makes this much more manageable. Your outside is that the stuff is being raised to the 5th power. The inside is 2x minus 5. So to take a derivative here, to take the derivative of the outside, it's just something to the 5th power. So we got 5 times stuff raised to the 4th power. Right? And that stuff, the 2x minus 5, just stays the same right there. Don't do anything with it. And then we must multiply by the derivative of the 2x minus 5. What is the derivative of 2x minus 5? Just 2. Here. And they will clean that up a little bit. All of that stuff is multiplied 5 times 2x minus 5 to the 4th times 2. So we can multiply the 5 and the 2 together and just get 10 2x minus 5 to the fourth as our final answer. And they will not expand that. They'll leave the answer choice looking like that. Okay, 5 gets a little harder. For 5, do I need, where's my outside, where's my inside stuff here? There's a chain rule necessary. Inside's definitely x squared. I think the inside is a little bit easier to find than the outside sometimes. Because a lot of times it's in a set of parentheses somewhere, right? Or inside of a square root. That's our inside. Our outside is the tangent. Okay? The 2x is not part of your outside. You could include the 3 or not include the 3. It's up to you. It's just a coefficient. These two things you're taking the derivative of separately. What is, because they're separated out by plus or minus signs, right? So if you have terms separated by plus or minus signs, you take the derivative of them separately. So when I take the derivative of 2x, what is it? 2. Okay? So it's not part of the chain rule. It's just a regular, power rule happening there. I'm going to choose to do this. I'm just treating that 3 like a coefficient. It just kind of hangs out front for that. You can put it with a tangent. You can do it either way. It is just a coefficient. So if you lump it in with the tangent, it's just a coefficient in front of the tangent and doesn't really change how you do it. It's just going to sort of hang out there. Or you can not. Either way, it's going to work the same, no matter how you think of it. So when you take the derivative of tangent, this is going to test our memories here. What's the derivative of tangent? Secant squared. So derivative of tangent is secant squared of stuff, right? The stuff is x squared. We do not take the derivative of it here. So the blue box has to stay the same in that first step. But then we must multiply by the derivative of the stuff. What is that? 2x. All right, they'll clean it up a little bit. They won't do anything too crazy with this, I don't think. But that 3 is multiplied by your secant squared. This stuff is multiplied by 2x. So they're going to combine the 3 and the 2x there together and probably put it up front. So your h prime of x is going to be 2 minus 6x secant squared of x squared. Okay. Questions? I don't think so for this. I think they'd leave it. There's a chance they do something like secant 1 over cosine, so they might make it like 6x over cosine x squared. I don't think they would, though. I think they'd probably leave it like this. Okay, how are we doing here? All right, let's do a few more. And then we got to look at some logs and exponentials, which sound bad, but are actually pretty easy. All right, now.
Is that 3 part of the cube root?
Yes, this is a cube root. It is not close enough because the program I was using for this doesn't do them very well, so I shortcutted it for that. But this is supposed to be a cube root of x squared minus 1 squared. Now, if I do it like it is right here, this is a triple chain. All right, you got a cube root, you got a square, and then you got an x squared minus 1 on the inside. So that would be, you'd have to do the chain rule twice on that. However, if we can avoid doing the chain rule twice, it'd probably be best to do so, because the more times you have to do the chain rule, the more likely you are to make a mistake with something there. So there is a way I can rewrite this so that I only have to do the chain rule 1 time. What do you think, Connor?
Do you make it like x squared minus 1 to the 2/3?
Yes. So I am going to rewrite, I'm not taking the derivative here. I'm going to rewrite this as x squared minus 1 to the 2/3 power. It will be much easier than trying to do the chain within a chain. Chain within a chain is never easy. It will work if you do it that way. It's just going to be harder. And, like, just to explain why that works, if I was going to do chain within a chain, I'd need to make it to the 1/3 power anyway. So I would have x squared minus 1 squared to the 1/3 power. And when I do powers to powers, like here I'm taking that second power and raising it to the 1/3 power. What do I do with the exponents? Multiply them together. 2 times 1/3 is 2/3 there. So our outside box is to the 2/3 power. The inside box is the x squared minus 1. So to take my derivative here, I start by taking the derivative of the 2/3 stuff. So I got 2/3 gets multiplied out front of stuff raised to the, what power is it going to be? You got to do 2/3 minus 1. What did you say? Not -1. 2/3 minus 1 is 2/3 minus 3/3. -1/3. There. And stuff on the inside here stays the same. Stuff, of course, not being the proper mathematical term for that. But I think it helps to put that in last. So now, stuff on the inside stays the same, but then I must multiply by the derivative of the stuff on the inside. What is the derivative of my inside function? 2x. Now, I do find students struggle with fractions simplifying here. For this, what I suggest doing is make everything a fraction. Every single piece needs to be a fraction. 2/3 is already a fraction. Put this over 1, make it a fraction. Put this over 1, make it a fraction. Okay? So, if you want, you could send the -1/3 down to the bottom of this fraction right here. So, that's going to be 2/3 times 1 over x squared minus 1 to the 1/3 times 2x over 1. And then, when you're multiplying fractions, you're just multiplying straight across. In the top, you're going to get a 4x. In the bottom, you'll get 3 times x squared minus 1 to the 1/3. Or they might change that 1/3 power back to a cube root. I'm running out of room here, sorry. Like that. Just, it doesn't really matter whether you make it a 1/3 power or a cube root. It just matters what the answer choices look like. If it's a free response, it doesn't matter.
Where could we have just left it? As a free response?
Technically, here. Right there. That on a free response, you technically, as soon as you have completed it, you don't have to simplify it all. Now, a lot of times, it might be helpful to clean it up at least a little bit to answer. A lot of times, they'll ask you to use it again to write the equation of a tangent line or find a horizontal tangent or something like that. So, sometimes it's helpful to clean it up, but technically, you can stop there. Okay? 7. For 7, it looks like a quotient rule problem. But, what can we use so that we don't have to do a quotient rule? Negative exponents. So if I rewrite this, it's still g of x. It is not g prime of x yet. As there's a negative out here, so I'm going to say -5, parentheses, 3x minus 4 to the -2 power. And so if I rewrite it this way, I can use chain rule instead of having to use quotient rule. So the outside is the -5 times the stuff raised to the -2 power. And the inside is the 3x minus 4. Okay, so when we take the derivative of the outside part, that's the -5 stuff to the -2 power, right? It's power rule. So -2 times -5 will give us a +10 of some stuff on the inside to the -3 power. And that stuff on the inside, our 3x minus 4, stays the same. But we must multiply by the derivative of the stuff on the inside. What is that? Just 3. Just 3. Right there. All of that stuff is multiplied together. So I could multiply the 10 and the 3 together. So 30. They might write it like this, 30 times 3x minus 4 to the -3. They might leave it with negative exponents. What you're probably more likely to see is then move it back down to the bottom and have 3x minus 4 to the 3rd power. So you will see some on your assignment that are going to look like they're quotient rules, but they could be transformed into a chain rule for that. Or they could be done with the quotient rule. You can still do it with quotient rule. It's just like this is going to have a lot more difficult simplifying if you do quotient rule on this. It kind of like simplifies itself if you use chain rule. Because all you really have to do is put the 3 and 10 together and move this back down to the bottom here. This way. All right, we do need to look at logs and exponentials. So we have already talked about the derivative of a log. It is 1 over x. So if we have a chain rule with a natural log function, the derivative of a natural log, here I've used a u instead of an x, and this u represents any other function in the world. It could be sine of x. It could be x squared minus 3x. It could be 2x. It could be anything, right? Anything besides just an x. So if I have natural log of something, then my derivative is going to be 1 over the natural log, or 1 over that something, times the derivative of the something. Right? So, what throws kids on this is it feels like there needs to be a natural log in your derivative, and there is not. So, a lot of times kids will put a natural log in there somewhere, and it's not supposed to be there. So, whenever we look at a problem like number 8, the outside is the natural log. That's our outside box. And the inside is the 3x plus 2. So to take your derivative here, when you take the derivative of natural log, it is 1 over the something, right? Which the something is 3x plus 2. That takes the derivative of the natural log part. Then you must multiply by the derivative of the something, the stuff on the inside, which is just 3 here. Again, fractions throw kids sometimes, but if you have a fraction and other parts that aren't fractions, just make everything a fraction. That 3 is a 3 over 1, right? And then just multiply straight across 3 over 3x plus 2. Can I simplify any further? Maybe tempted to mark those 3's out, can you? You cannot. You just have to stop here. In general, these can be difficult if it's like a natural log shows up inside of a product rule or something like that. It can be pretty difficult. But if it's just a straight natural log, they're usually fairly straightforward for that. Exponentials are also pretty easy, but kids mess them up a lot of times because they forget they even have to do the chain rule with it. So the derivative of an exponential is itself. But if instead of having x, you have a u, oh gosh, let's erase that. Instead of having an x, if you have a u instead, and that u represents any type of function, it could be negative 3x, it could be sine of x, it could be x squared minus 4, whatever, it could be any type of function, then it is still itself, but you must multiply by the derivative of whatever that exponent was for that. So if we're looking at example 9, the outside is the e to the x, or e to the stuff part. The inside is whatever is in the exponent. There. So, to take this derivative, the derivative of an exponential is itself. So, e to the stuff, the derivative of e to the stuff is e to the stuff. Okay? The stuff stays the same. Right there. But then you must multiply over here to the side by the derivative of the stuff, which in this case is negative 3. They will rewrite this and write it as negative 3e to the negative 3x. There's also a chance they do something else with this. How else could you write that? Negative 3 over e to the 3x. Since that does have a negative exponent, they could move it back down to the bottom. They might do either one. Just be prepared to see either one of those. Okay, questions? Okay, we're stopping here for today. Because after this, we got to do product rules with this. And we got to do chain rules inside chain rules. And we got to do quotient rules. But for today, we're going to practice this. And then when we got this, we can go on to those things that are a little harder. So, your assignment is there at the end. You've got a good amount of time. Hopefully, you can get it done.